All righty, folks. How we doing today? How we doing? All right, so we're gonna move into our fourth out of our five analysis chapters before we turn and look at trig a little bit. And what we're gonna look at today is something called, we're gonna get introduced to something called conic sections. So this fourth chapter is gonna be dealing with something called conic sections and systems of equations. So today we're gonna start off, we're gonna learn about two different conic sections, circles and parabolas. So now there's four conic sections. We'll get to the other two here in a little bit, but we're going to be dealing primarily with these first two today. So to begin with, let me go ahead and kind of just talk briefly about what a circle is here. And again, a lot of you like going, Williams, I know what a circle is. Yeah, I get that, but let's just, for the fun of it, let me just assume that we are missing a little bit here. So a circle essentially is some point, some set of points that if I were to spin this around this point, the origin 0, 0, or around some set point, when I spin it around there, that looks pretty good. When I spin it around that point, I create all these other points. So if we look at this thing as far as like a series of x and y's, and I were to drop this down here, notice really a circle is made up of an infinite number of squares, infinite number of triangles that have the same radius. So we say, all right, well, let's let that radius be, or let's let that triangle be some form of a whole bunch of Pythagorean theorems. So x squared plus y squared equals r squared. And that's kind of what we've been dealing with for a while, right? But just for the sake of argument, what if I were to take my center of my graph like this, and I were to move it, so now it's no longer at the center, it's been shifted over. So it's been shifted over some units to the right, and we'll call those units to the right. It can be shifted to the right or to the left, it doesn't matter. We're going to call that h. And then it can be shifted over some units up or down, doesn't matter again, we'll call that k. So again, it's like moving our transformations that we were dealing with at the beginning of the year. It's just instead of calling them C and D, now we're calling them H and K. And so then we get to what we have, the general form of a circle. So X, and then anything in parentheses we said always gets the opposite sign. So we're affecting the X by moving it H units to the right, and we're affecting the Y by moving it K units to the left. And we end up creating this standard form of a circle. So we'd say then that the center of the circle is always going to be located at H and K, and the radius of the circle is always going to be the square root of that number, that R value, because that's the distance it is from the center. So to begin with, today we're just going to start with this idea of circles. So say I give you one, x plus, let's do x minus 2 squared plus y plus 1 squared equals 9. So here's what I want you guys to do. I want you to tell me the center. I want you to tell me the radius length. And then I want you to go ahead and graph the dumb thing. So let's just graph it when we're done there. So go ahead and pause it and let's see what you guys can come up with. Yep. All right, so let's see how you did here. Notice we said, that's a plus right there. I should probably make that a little clearer to read. Oop, there we are. So the center, we always said it's like setting those factors equal to 0. They always end up getting the opposite sign. So the -2, that would become a +2. The +1 here would become a -1. So that's our center. And the radius is always the square root of the last number. So the square root of 9 is 3. And again, we did this back in integrated 2, so it's not new and stuff we've looked at before, but it's been a while. So we're just not going to take anything for granted here. We're just going to go ahead and deal with this like normal. So we're going to graph our center. So 2, -1, so over 2, right 1. And now our radius is 3. So we're going to go in every direction 3 units, 3 to the right, 3 to the left, 3 up, 3 down, and we are going to graph our radius. So there's 3 to the right, 3 down, 3 left, and 3 up. And by creating that now, we can go ahead and connect the dots. Now you guys are going to probably draw a lot better circles than I am. We end up creating a circle-ish type of idea. So let's keep going on this idea of a circle here. What if I give you something, instead of being in standard form, what if I give it to you in general form? So x squared plus y squared plus 6x minus 4y minus 3. So we need to put it into its standard form. Now, in order to get it into standard form, we're going to get rid of that constant number to the other side, and we're going to group up all the variables. So once you're there, then you're going to complete the script. You guys have done this before, so I'm going to go ahead and give you a chance. Pause the video, try it, and then we will come back and try to refresh our memories if we need that. All right, so here we go. I'm going to group all my x's together. They're all in Texas somewhere, but that's another story. I know, bad joke. Bad joke. Whoop. There we are. We always, whenever we group up on these conic sections, and you'll hear this over the next couple of days as well, we always put a plus in between our parentheses. Now, it might not always stay there, but we always want a plus in between our parentheses. So I like that. We're going to move our 3 to the other side. And we have a radical, and not radical, a blank and a blank. So we're going to have to finish off the blanks here. So we're going to complete the square on our x's, and we're going to complete the square on our y's. So I'll start with the x's here. Whoop. And so we're going to take our x squared, it goes here. Remember the positive 6x, we're going to split up into 2 equal parts. So that 6x is going to be 3 and 3. Like that. And from there, we can go ahead and complete the square. And again, guys, if you remember the take the middle number, divide by 2, and square thing, feel free to do that. But if you like the visual, this is the visual behind completing the square. So the missing number is 9. So to make a perfect square trinomial, I needed to add a 9 into that side. And we're going to do the same thing with our y's here as well. So we're getting ourselves our y's here. So we had our y squared minus 2y minus 2y. And when we complete the square here, we have our y, our minus 2. So you can already start to see what these perfect squares are going to turn into. So that's a positive 4 that we're adding in. That makes that a positive 4 on the other side. So x squared plus 6x plus 9, well, that's x plus 3 squared. plus y minus 2 squared. And the whole thing is equal to 16. All right, so I don't want to assume everybody did that perfectly. So why don't you guys go ahead and pause again. And if you need to make any changes now to graph your, or to do your center and radius correct and then graph it, why don't you go ahead and do that? And then we will go from there. So go ahead and list it, and then we will go from there. All right, let's see how we did here. So my center is going to be that number that's opposite of x, so -3. Opposite of y, that's going to become a +2. That's my center. So again, we do the opposite of x and the opposite of y. And technically, they're not the opposites. We just would set those equal to 0 and use our zero product property to get those actual values. So there we are, whoop, right like that. And now we're going to go ahead and get our radius. So the radius is the square root of the last number. So the square root of 16 is 4. So now we're going to go off 4 in each direction. So up 4, 1, 2, 3, 4. Whoop. Right 4, 1, 2, 3, 4. Left 4, or down 4. It's close enough. Left, down, whatever works for you. Let's undo that one. I kind of missed there a little bit. There we are. There we go. 1, 2, 3, 4, and left 4. And now we're going to play connect the dots. I'm telling you, add some sound effects, and math just became more enjoyable. All right, well, we're just about done with centers. And again, or centers, circles. Again, this is review for a lot of you guys, right, from integrated 2. So hopefully it's not too terribly bad there. And what if I give you just a little bit more information? Let's try a little bit more here and just see what you guys have come up with. Determine the equation of the circle with a center at, oh, let's make that center at, let's go -2, 0. So put the 0 there, and passes through the point. Oh, let's make that, just for the sake of it, let's make that -5 and 4. All righty. Why don't you guys, first of all, I recommend draw a picture and then see if you guys can determine what the equation looks like. All right, you pause it, try it. All right, let's see what we did. All right, so to begin with, I'm going to go ahead and try to come up with a little bit here. I know my center is at -2, 0, so I'm going to go ahead and draw my center. And I know I have a radius, or a point at -5, 4. So 1, 2, 3, -4, -5, 1, 2, 3, 4, right about here. So that's my radius value. So let's see here. If I know that's my radius value, or an endpoint, that means my radius is going to go all the way out to that. So I might be able to figure out where that R value is. So just like we did before, if I draw myself a triangle, it's not necessarily down to the x-axis. It's only going to the x-axis because that's where my center is. I have a triangle with a base of 3 and a height of 5. And you guys probably can already tell what Pythagorean triple that is, but just in case, we'll do the Pythagorean theorem here real quickly, just to figure out what that R value is. So we have 9 plus 16. So 25 equals R squared. And honestly, we could stop there, but just because I'm going to keep going a little bit more, 5 equals R. I'm telling you, I struggle. I've been struggling all year trying to write a 2 with the mouse, man. It is not the easiest thing in the world. Got a little bit better at it, but not the easiest thing in the world. All right, so We're going to go back to our original equation, x minus h, so we're going to have that here, plus y minus k, we'll have that there, equals the r squared. All right, so we're going to plug in our values here. So the x value of my center, that was -2, so we'll plug in a -2 here. The y value of my center, that was 0, so we'll plug a 0 in right there. That's my h, my k. And then we found the radius to be 5, so plug in 5 right there, and I end up with the equation x plus 2 squared plus y squared equals 25. All righty, so friends, those are our circles, all right? Those are our circles. So we're going to move on a little bit more now because the idea of parabolas take up a little bit more time here. Because we're not going to look at a parabola like we've looked at it before. We're going to look at it in terms of the conic view, the conic section view of it. And again, you guys are probably asking, what's a conic section? I'll show you that here in a second. I call them conic sections because if we were to take them and put them into what they call a conic plane, in other words, two cones that intersect. So imagine I have two cones here, and these are going to intersect. If I were to take some sort of plane, and what I mean by plane, not like a plane like you might be thinking of here, but a plane like a sheet of paper type of plane, and I were to go through and cut that shape, what it ends up creating is, see if I can't get that to fit a little bit better here. Ends up creating some sort of shape like we just saw there, where it was turned into a circle. So depending on how that thing slices this cone, two different cone plane, it creates these shapes. So in this case, it would create a circle. Now, if I were to have cut this shape in a different way, say like I were to cut it going down like this, so it's parallel to a side, like that. What ends up happening there then is, and again, I get that it's a little hard to visualize, is I would have created a parabola. So if I were to tilt that plane a little bit, I would be able to create a parabola when I cut through. And so the other two shapes, we'll look at one shape each of the next 2 days, but today's the day we're looking at two shapes. So now we're looking at a parabola. What happens when we cut a parabola in half? Or not in half, but cut out a parabola. What things pop up? Well, for instance, if I throw a parabola on here, turns out that the x-intercepts and the y-intercepts, those are all hunky-dory, but they're really not terribly important in the grand scheme of parabolas. What is important is this point right here, this relative min or relative max, and we call that the vertex. And again, that's not new. All right, we called it a vertex before. But these parabolas, they're designed in a very, very perfect way. They're designed in such a way that all the energy is focused around a given point. We call that point, well, miraculously, we call it the focus. We'll talk about that point here in a second. But every parabola has been designed in such a way where if I were to take any, and again, I did not draw a great demonstration of what this parabola is. If I were to take any point on a graph of a parabola, right here, the distance from its focus is the distance from some different plane, some different line that is going to be essentially perpendicular to the line that goes through the focus and the vertex. So that line that I just drew there, even though it's obviously not the same on mine, that line would have been the same distance to this line down here. So this distance right here would have been the same as that distance right there. Parabolas are designed so amazingly, so specifically that they have the opening go a certain length. Now, your satellite dishes and all the different things that we use with satellites, they're designed with this idea in mind, and they have to be designed just perfectly so that way when all the rays come and they hit, they come down and they hit the parabola, they always go back to where that receptor is, which is where the focus is. So turns out that we have some things that we can talk about here. So it turns out the distance from our focus to our vertex, we call that our p-value, is a distance, the same distance to this line, this imaginary line down here, which we call the directrix. And I'll show you more about that here in a second. So those are both equal to p. They're the same distance. Likewise, this distance that goes out here from here to here, turns out, if this is going 2p units down, then this line that goes straight out is also called 2p units as well to both those sides. And so it's a way for us to design how wide to make it. If I know what my p-value is, I can figure out how much to count out to the left and to the right to determine the length of my parabola. Let's see if I can get rid of that circle right there. Apparently I can't. Oh, I can. Hey, very cool. All right, so now every time we're in class, you folks tend to giggle a little bit when I say the name of this. So hopefully we're not going to giggle on the video here, but that distance from here to here, that 4p value, we call that the lattice rectum. So it is the opening, the rectum of the actual parabola. So the lattice rectum. All right, so when I put all this together here, turns out we're used to equations looking like this. A times x minus h squared plus k. Well, this a value, mathematicians have found out it's equal to 1 over 4p. And you can see where that 4p came from. That's the length of the lattice rectum. So if we were to just throw that in there then, in place of that a, and make that 1 over 4p, we can start to play with this equation a little bit. So let's move the k to the other side. Y minus k equals 1 over 4p, x minus h squared. And if we were to multiply both sides by 4p, we'd get a different way to write a parabola. This is considered the conic section way to write a parabola, because it tells us 4p, it tells us the length of the opening, the rectum, the lattice rectum. It allows us to figure out that focal length, that p value, so the distance from the vertex to the focus, and also the distance from the vertex to the directrix. So if I were to throw all that in here, I get an equation that looks like this. So 4p equals y minus k equals x minus h squared. And then we get some information about it as well. So the vertex would be the h and k, still just like it was before. But now we have this focus. Notice the focus, it has the same h value, the same x value. So the only thing that changed is we added p to the k value. The directrix, well, that's a horizontal line, but it's p units the opposite way. So y equals k minus p, since y equals any number is a horizontal line. And then the length of the lattice rectum is always going to be equal to 4p. Just like that. And we can make the same argument, the same type of argument for a parabola that is opening to the side. Now, you guys called that a sleeping parabola in integrated 3. Oh, that name kills me. Parabolas can't sleep, friends. They just can't. All right, they're inanimate objects. All right, they don't sleep like you and I do. So let's just draw a real quick one so we can see it, and then we're going to play with it a little bit here. All right, so say I have a parabola looking like this. Whee! All right, a nice non-function parabola is a better name to call it, not sleeping. Notice it's going to have a vertex too. It's going to also have a focus. It's going to have the links going out from the lattice rectum. And it'll have all this still the same. So that means the distance from here is p. Distance from here is p. And 2p and 2p. Not to be confused with 2b or not 2b. That's a different question altogether. So now notice on this one, all the stuff's the same. It's just the p now is going to affect the x value, the h value, not the k value. So if we were to go through and write all this stuff out, we would have found out that it just changes a little bit. Instead of 4p being with y minus k, it'd be with x minus h. And the y minus k would be on the opposite side over here. Notice they're both in parentheses, therefore when we write it, we always change the sign. And we have all of our information again. So let's write that in there. Vertex, still h and k. Oh, let's see here. Directrix, focus. We'll call that h plus p. By the way, if your p value is positive, it opens up or to the right. If p is negative, it opens left or down. Okay, so the p is also going to tell us the direction too. The directrix. And then the length of the lattice rectum is still the same. Still 4p. All right, so that is really what we're going to play with here today. So to begin with, let me give you guys an equation. Nice, straightforward, simple equation here. And I'd love for you guys, if you don't mind, I'd love for you to go ahead and graph that. So say I give you an equation like this, -8 times x minus 1. So whatever is squared, you're going the opposite direction. So if x is squared, you're going up and down. If y is squared, you're going left and right. So let's see if you guys can play with this idea here for a second. All right, using this, see if you can find the vertex, the focus, the directrix, the length of the lattice rectum, and then try to go ahead and make a sketch of the graph. Go ahead and pause the video and give it a shot. All righty, let's see what we did here. First up, let's deal with the p-value. I always try to find the p-value first. So notice, That's always the number right here, 4p. So here's 4p. So that means that's the 4p value. So if negative 8 is 4p, that means negative 2 equals p. Yeah. To find my vertex, there's my x, there's my y. We're just going to flip the sign. So my vertex then, instead of negative 1, I'm going to have a positive 1. Instead of positive 2, I'll have a negative 2. The p-value says, or for my focus, I'm going to take my 1, and I'm going to add my p-value to it. So I'm going to take 1 plus whatever my p-value was a negative 2 here. And I'm going to add it to, or whoopsies, need to make that green again. There we are. And then my k value, which was a negative 2. So my focus then was negative 1, negative 2. My directrix, since this is going to be going left and right, my directrix is going to be a horizontal or a vertical line. So it looks like we treat it kind of like an asymptote. It's not an asymptote. We treat it kind of like one. So we have our negative 1 right there. And this time I'm going to subtract my p-value. And let's see here, that would be x equals a positive 1. Oh, one thing I did forget to add here, I should probably throw it in there real quick. The length of lattice rectum, it's always the absolute value of this, by the way. You can't ever have a length that's negative. So my length of my lattice rectum then, it's going to be the absolute value of 4 times negative 2. So that's a negative 8, which would be positive 8. And we can see that because that's what this was. Just take the absolute value of the original value. All right, so that means when I do graph that lattice rectum, I'm going to go 4 units one direction, 4 units the other direction to keep it symmetrical. So now we can go ahead and we can graph our points here. Let's see here. I got a focus that's negative 1, negative 2. I'm going here. And 1, 2, 3, 4, 5, 6. All right, so the vertex, we'll graph that first. So where we have vertex 1, negative 2, that'd be right about here, vertex. My focus is negative 1, negative 2. All right, well, where'd that be? That's here, focus, negative 1, negative 2. Oh, I just realized I have I should have been a positive 1 down there. All right, so focus is negative 1, negative 2. So we're going to go through and graph that. Negative 1, negative 2. Here's my focus. Notice how it's 2 units away. And so I'm going to go 2 units away the opposite direction. So x equals 3. So since my lattice rectum is 8, I'm going to divide by 2 to get 4. So I'm going to go out 4 units. Since I'm going left and right, I'm going to go up and down 4 units to get my points on the parabola. So 1, 2, 3, 4. So it's going to open up here. And 1, 2, 3, 4, right about here. And while we have a really good idea now of what this graph looks like as far as the actual dimensions of it, like that. All right. Well, there we go, folks. I'll tell you what. Let's try another one here. What if I give you something like this? Let's go 0 equals, excuse me, x squared minus 2x plus 4y. There you go. And plus 9. Right there for you. And friends, why don't you go ahead and give that a shot there and see if you can come up with the circle, the equation of the circle. So go for it, and I will talk to you in a little bit. All righty. Let's see how you did there, folks. Let's see here. 0 equals x squared minus 2x plus 4y plus 9. So when we're actually going through and dealing with this, whatever is not squared, that's going to be the thing we want to kick off to the other side. So the 4y and the 9 are going to go to the other side. So let's go ahead and do that now. So negative 4y and minus 9. And that, if I need to factor anything out of the x squared side, I will, but that's going to be the side that I have to complete the square on. So if you didn't get a chance to do that, why don't you go ahead and complete the square there real quick and pick it up and see what you come up with. All righty, let's see here. See how you did. I have an x squared. Splitting that 2x in half here like that and like that. So we have our x, our minus 1, and a minus 1, like so. And that means I'm adding 1 to this side. So I'll add 1 up here, and I'll add 1 back here. So I have negative 4y minus 8 equals x minus 1 squared. So there's, got that side all put together. The only thing I have left to do is notice the y minus k here. Y minus k is in parentheses. So that means I need to factor out that negative 4 from both those terms. So if I do that, I get negative 4 and my y plus 2. So this is going to be an up and down parabola. All righty. So let's go through and let's try it. First thing you know what I'm going to probably do is get the p-value. So that's my p-value right there. So negative 4 equals 4p. So negative 1 equals p. All right, we're good at that. So now the vertex, that's going to always be the opposite signs. I actually think that parabolas are also easier to graph when they're in their conic section. I know they look a little bit different to you guys coming out of algebra, but I actually think they're a little easier to graph and make them more accurate. So 1 and negative 2. So the focus is going to be affecting the k value this time. So 1, so negative 2 plus a negative 1. So that means my focus then is 1, negative 3. And my directrix, that would be y equals the k value minus my p value. Which would be y equals negative 1. And then the last, and certainly least, the length of the lattice rectum. That is the absolute value of 4 times my p-value. And again, we already have this one up there already. So 4 times -1. I'm taking the absolute value of that number. So it will be 4. So it's going to open up to both directions. So since I'm going left and right, I'm going to make sure that I open up 2 units going both. I'm sorry, since I'm going up and down, I'm going to make sure I open 2 units when I go left and right. So, all right, let's graph it. One, 2, 3, 4, 5. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. The next couple conic sections we'll spend a little bit more time with because they're a little bit more unfamiliar to us. But we can go through and do a real nice quick review here and kind of grab most of this here. So the vertex was 1, -2. And let's see here. Then we have our focus, which was 1, -3. It's literally right below it. And then y equals -1. Like that. There's our directrix. And then since I'm going up and down, the opening, the lattice rectum will go left and right. So I'm going 2 to the right and 2 to the left. And now I can connect the dots. Just like that. All righty, friends, we're going to have one more itty bitty teensy weensy little problem for you here. One more little problem. We got all this information we've been playing with here. What if I were to give you a different scenario? Determine the equation of the parabola with a directrix of y equals -1 and a focus at -2, 5. All right, here's my little key for you. Graph it, see what you come up with, and then we'll talk about it. Go and pause the video and give it a shot. All righty, let's see what you guys came up with here. First thing I gotta do is figure out, are you going up and down or left and right, or which way are you going here? And that's always the hardest part. So I have a directrix at -1. So here we go, -1. I can already tell, since my directrix is a y value, I'm going up and down. That's going to help out in a second. And my focus is at -2, 5. So 1, 2, 3, 4, 5. All right, so I am going up and down here. So that means I'm going to go with the 4p being linked up with the y. If I was going left and right, 4p would be with the x. So let's see here if we can figure out what that p value is, what that k value is, and what that h value is. If we can, we are sitting pretty. So the biggest question that's going to come up is, where's the vertex? And remember that the vertex is the same distance away, that p units, that same distance away from the directrix and the focus. So in other words, where's the middle of it? The middle of it would be right here. Because now I have a distance that's 3 units away. And 3 units away. So I know my p-value is 3. The question is it a positive 3 or a -3? So the answer for that is, if it goes up, it's positive 3. So p is going to be a positive number. If it goes down, then it's a negative number. And likewise, you do the same thing with left and right. So that's going to be a positive 3 there. My vertex then is going to be at -2 and 2. So minus a negative, or -2, I guess that is, and minus a -2. So we have those values. And so now we can go ahead and finish writing the equation. So 12 equals y minus 2 equals x plus 2 squared. All righty, folks. Well, that takes care of the first 2 of our 4 conic sections. You guys had an educational opportunity this morning, so we'll talk more about this tomorrow morning. So hopefully this gives you a good start, and we'll see you then. All right, take care.